Alright guys, this video is going to focus on 5.3 and 5.4, which deals with finding intervals of increasing and decreasing, and then using the first derivative test. So this first slide is really just a summary of what we've talked about with, EVT, the extreme value theorem. So key thing, f is continuous on a closed interval, and they broke these steps into two pieces, whereas we just did it as one. So you'll find your critical numbers. Remember, that's where f prime of x is equal to 0 or undefined. You'll evaluate each of those critical numbers and the endpoints in the original function. The highest is your max, the lowest is your min. So that's what we've been working on. All right, so definition of a critical number. Once again, we've already talked about that, but a critical number is where you set your derivative equal to 0 or where it's not differentiable or undefined. So, for example, in this graph, okay, it's not differentiable at that sharp corner or cusp, but here, this is where the derivative is equal to 0. So both of those would be considered critical numbers. So relative extrema occur only at critical numbers. So relative extrema, remember, that's just in those local neighborhoods. They're not necessarily on closed intervals like the absolute extrema were. So if you look at this, you can see, hopefully, that this is a graph of f of x, the original function. This whole section right here, we are increasing. And then after that, we are decreasing. And we have a relative maximum here at the point 0, 0. Then, so we were decreasing, and then here we're increasing again. So here at 2, -4, we have a relative minimum. Okay, and those are like the mins and maxes that I think we're used to talking about from like pre-calc and stuff like that. So, definitions of increasing and decreasing. So if a function f is increasing on an interval, if any two numbers x1 and x2 in the interval, if x1 is less than x2, that implies that f of x1 is less than f of x2. So that's a lot of words. So let's come over here. Let's say I call this x1 and this x2. And I set that up so that x1 is less than x2. When I go up to the graph here, this would be the point f of x1. This would be the point f of x2. You can see, since it is increasing, f of x1 is less than f of x2. If it's decreasing, so I'm going to, instead of x1 and 2, I'm going to call this like x3 and 4. Okay? I made sure that, like I said, x3 and 4, so x3 is less than x4. Here, when I go to the graph, what's going to happen is the flip, f of that x3 is going to be greater than that x4 if our function is indeed decreasing. Okay, so when we look at this, it says over what intervals is f of x increasing and decreasing. So take a minute, pause the video, see if you can figure out the intervals where we're increasing and decreasing for both of these. All right, so if we take a look here, hopefully you said that we have this relative minimum here at this point. It looks like 1, -9. I know it didn't ask for that, but so we're decreasing from -infinity to 1, and then we're increasing, and you want to actually include 1, and we'll talk about that more on Monday. And then we're increasing from 1 to infinity. Okay, on this guy, you have this relative max here, and this relative, I think it's at 0, 0. Let's make it at 0, 0 for easy sake here. So you can see that this graph is increasing from -infinity to -2, but then it decreases from that -2 to, it looks like we have a VA here at -1. Now, it's decreasing to -1. And then we're increasing, we're decreasing, my bad, from that -1 to 0. And then we're increasing again from 0 to infinity. And we'll talk about the whole open close bracket idea with these. Clearly infinity and negative infinity always get the open bracket or the parentheses, but we'll talk about that more on Monday. All right, so to test for increasing and decreasing, we can look at our derivative, which tells us about our slopes. If our derivative is greater than 0, aka positive, that means our slopes are positive, so f was increasing. If our derivative is less than 0, aka negative, that means that our slopes were negative, so f was decreasing on that interval. And if it comes out equal to 0, it's just constant, or it could be like the turning point. So a couple things that I want to add here. Critical points. Critical numbers, critical points, same thing, are the only place a function may change from increasing to decreasing or vice versa. So I'm going to show you a couple different pictures here and why I emphasize the word may. So if I have something like this, so I think we're all clear that this is a relative max, and if you think about it, it was changing from increasing to decreasing. Here we have a relative min, and we're changing from decreasing to increasing. And these 2 points would have showed up as critical points because that's where f prime of x is equal to 0. But I have a graph like this, kind of like your standard cubic. If you think about it though, here I'm increasing. Here I have for that brief second at 0, a slope of 0, but then I continue increasing, okay? So we didn't actually change from increasing to decreasing or vice versa. This guy's increasing the entire time here, okay? Then I have a graph like this. This one's gonna be a little funky here. Ooh. Okay, so here my slopes are negative and then positive, but I have a cusp. This would be a point where the derivative is undefined or not differentiable. Now, that still is going to be a relative minimum for us, okay, but that's how that would show up. Here we'd have the relative maximum. That's where the derivative's equal to 0. And I was trying to show here, this isn't a greatest picture, a vertical tangency here for a second. Remember, functions aren't differentiable at sharp corners, cusp, discontinuity, or vertical tangencies. We haven't really talked about that. Now, it's decreasing and decreasing, so that'll show up as a critical point, but it's not necessarily going to create a min or a max there. And then here's another point. We have another cusp where it's not differentiable. And then I'll show you, sorry, one more, where I have a VA. Okay, so here, f of x is undefined at that VA, and f prime of x is going to be undefined at that value of that VA also. Okay, so we can talk about the functions increasing here. It's also increasing here. They all have positive slopes, but we don't necessarily have any mins or maxes. All right. So guidelines for finding intervals in which a function is increasing or decreasing. We'll locate all of those critical numbers, use those to determine test intervals, and I'll show you a full-out example here in a second. Then we'll determine the signs of f prime on each of those intervals, and then we'll use theorem 3.5 to determine if it's increasing or decreasing, and that's just looking at the slopes. Okay, and then we'll figure out the intervals where it's increasing, decreasing. At the same time, we have the first derivative test, and we've talked about this already, so hopefully this makes sense. If f prime of x changes from negative to positive, so say you have negative slopes and then positive slopes, well, it must be occurring there is a minimum. Vice versa, if we change from positive slopes to negative slopes, what must be occurring there? A maximum. Now, if it's positive on both sides or negative on both sides, that's not necessarily a min or a max, and we saw that above too. So here you can see a min, or you can see a max. So here you see the slopes stay positive the entire time, so that's a critical point, but it's not necessarily a min or max. Same thing here. They're decreasing the entire time. That's a critical point, but not necessarily a min or max. The min or maxes occur where the signs actually change. So let's go through this example. So this is a very, very basic example. It says identify the intervals where it's increasing, decreasing, and state any relative extrema. So if we find our derivative, let's go for those critical points. We get 2x minus 4. That's not undefined anywhere, so let's just set that equal to 0, and hopefully we're all okay with 2. So we're going to set up this little sign chart here, and we're going to put any of our critical points on that sign chart. And then we want to test around that point in the derivative, because the derivative will tell us if our slopes are positive or negative. And I don't really care about this specific number, just are they coming out positive or negative. So let's plug in, I don't know, say 0 to the derivative. I get out a negative value, so that means I have negative slopes on that side. If I throw 3 into the derivative here, 2 times 3 is 6 minus 4, that's a positive. Once again, I don't care the specific number. That just tells us we have positive slopes. So if we have negative slopes, that means we're decreasing from negative infinity to 2. Then when we have positive slopes, that means we're increasing from 2 to infinity. If we decrease and then increase, that means that we have a relative minimum at that x value of 2. Now, if we wanted to find the whole ordered pair of that minimum, we would plug 2 back into the original to get the y value that goes with that point. So when we do that, we get 4 minus 8 plus 5, so we get out 1. Okay, let's look at another one. I'm going to skip over that one for a second, and I'm going to come over to these side examples here. So this one just purely asks for intervals of increasing and decreasing. So if you want to pause the video and try it on your own, by all means, go for that. Let's find our first derivative. It's not undefined anywhere. Let's set this equal to 0. Hopefully we're all okay with getting plus and minus 5. So we'll put both of those on our little sign chart, and we'll test around those. And you can pick any value that's in between the intervals. So, and once again, I don't really care about the specific value, just the sign. So if I put in negative 4 squared, so that's 16 times negative 3, this is going to come out positive. Hopefully we can all see that. If I plug in 0, hopefully you can see that did I mess up my sign? Oh God, I am so dumb. Don't plug in negative 4, silly goose. Plug in negative 6. That was bad on my part. Okay, so negative 6 squared is 36 times that negative 3. So the negative is going to be bigger than 75. So this region's negative. That was so bad on my part. All right, plug in 0 here. Hopefully you can see that's positive. If I plug in 6 here, hopefully you can see that that's also going to be negative. So we're decreasing from negative infinity to negative 5, and then we're also decreasing again from 5 to infinity because we have negative slopes. That means our original function is decreasing, and then we're increasing in between there, negative 5 to 5. Once again, if you want to pause the video and try this one on your own, let's take this derivative. Okay, now I'm going to rewrite this so that I can easily see if I'm going to have, whoops, that's a 3, any points where this is undefined. So this is undefined at x equals plus and minus 2. Where is it equal to 0? Oh, my God, I'm rushing because I have to fit this in 15 minutes, and I did not multiply it by the derivative of what's inside. My goodness, I need to stop making silly mistakes here. Hopefully you can see that this is equal to 0 at 0. So let's line those up on my chart. Once again, I only care about if this is coming out positive or negative. So if I test, let's say, negative 3. So that would make my numerator negative. Now in the bottom, if I take that squared, minus 4, so I'm going to get 9 minus 4, so that's 5, so that's a positive. So overall, this is negative. If I test, say, negative 1, that makes my numerator negative, but my denominator is going to be 1 minus 4, which is negative 3, and the cube root of a negative is still negative. So overall, this is positive. If I test 1, now my numerator is positive and my denominator is negative, so that turns negative. And then if I test 3, that makes my numerator positive and my denominator positive, so this is positive. So we are increasing from, oh my goodness, negative 2 to 0 and 2 to infinity. And we're decreasing from negative infinity to negative 2 and 0 to 2. All right. Let's do one more real quick. So the functions given by this, at what values of x do we have a relative minimum? So let's take the derivative. We want to, it's not undefined anywhere. I'm going to factor that 3 out. I can't do math right now. I'm rushing too much. Set this equal to 0. So I get points negative 6 and 2. So if I line those up, find where I'm increasing and decreasing. So I'll leave this to you to try in your derivative here, but it's going to turn out positive, negative, positive. So it didn't ask about increasing and decreasing, but you can see we're increasing negative infinity to negative 6, 2 to infinity, decreasing in between those. And if we're increasing then decreasing, we have a relative max at x equals negative 6. Okay, and we have a relative min, which is what it asked about, at x equals 2.